Look, lovely to meet you all online. So I'm David Waite. I'm based in Sydney at the University of New South Wales. I'm also where I'm a professor, but I'm also a chairman and CEO of a centre in China called the UNSW Centre for Transformational Environmental Technologies, based in Jiangsu Province. This talk is based on work that's been done both at UNSW here in Sydney, but also with my colleagues in our centre in Yixing. And I'm going to focus in the next few minutes on a technology for desalination that's been purported to be low energy, low cost. And I'm going to pose a question of whether this in fact is the case. So it's a talk on the technology of membrane capacitive deionization and asking, is this low energy, reality or myth? Okay, so firstly, what is MCDI? It's a technology in which we pass salty water through banks of electrode pairs with the cations like sodium attracted to the cathode and the anions like chloride attached to the anode. We can run this technology in either constant voltage or constant current mode. We tend to use constant current. And in that mode, when we apply a voltage across a current across the electrodes, we attract the ions to the electrode of opposite charge in a process known as charging. We are using porous electrodes, and after a few minutes, the electrodes become full of ions. The electrical double layers in which those ions are being absorbed are at capacity. At that point, we change the direction of the current and discharge the ions into a waste stream. So I'll just show that more clearly in the next slide. So here we have one electrode pair. Salty water is coming in. When we apply potential, the ions go to the electrode of opposite charge. We produce clean water, as shown on the right. When those electrodes are at capacity, we reverse the polarity and discharge the ions into a brine stream. And if we time the plumbing right with the change in direction of current, we can get that clean stream and then a brine stream. So pretty straightforward technology. I've shown you the performance or behavior in one electrode pair, but we build modules that in fact have many hundreds of electrode pairs. Again, during the charging step, we produce our clean water. In this case, we're running at fixed current, so the potential ramps up to about 1.4 volts. We don't go too high. If we went above 2 volts or so, we would split water and waste energy. We don't want to do that, so we limit the voltage to about 1.4 volts, and we then reverse the polarity and discharge into a brine stream in this red section. As you can see, the times of charging, discharging are around 2 to 3 minutes for each step, but that charging time can vary depending on the amount of salt in the water. Okay, so let's ask the question up front: is MCDI more cost effective than the alternate technology, of which the main one is reverse osmosis? And the answer is pretty clear that it depends on both the salinity of the water and the size of the plant. So reverse osmosis is a great technology. The amount of salt in the water doesn't really influence the operating cost, shown on the left plot as kilowatt hours per cubic meter, whether the water's brackish or quite saline like seawater. We tend to use the same cost to operate that system. But in MCDI, that's not the case. The saltier the water, the more electrodes we need to remove the salt. And so as the salinity increases, as shown in this early paper by Oren, an Israeli researcher, as the salinity increases, the operating cost increases because we need more electrodes and thus more power to remove the salt. And so it's clear then that for really salty water like seawater, the cost of MCDI, and it depends a bit on which potential you drive it to, but let's say 1.2 volts, which is the sort of potential we're using. Once you get above about 1,000 milligrams per litre, MCDI becomes less cost effective than the reverse osmosis. So the technology is really only suited for removing salt from brackish waters down here below about 1,000, 1 to 2,000 milligrams per litre of salt. In addition, in terms of O&M costs, operating maintenance costs, large RO plants are very cost effective. So large plants are really the way to go if you want to desalinate large volumes. But small RO plants are really quite expensive in terms of operation and maintenance. And it's in this small plant size where MCDI has an advantage. And so brackish water, lowish salinity, plants that are small are really where this technology, we believe, has potential to be more cost effective and energy effective than reverse osmosis. And that's particularly the case if we could use potentially solar energy to drive the plant. And at 1.2 or 1.4 volts DC, this technology is well suited to using PV panels to power the units. And also potentially we can recover energy in the process. And I'll talk more about this in a minute. If we can do both of those, that is use solar energy and recover energy during the charging process, then we are a long way ahead of reverse osmosis in this plant size regime. Okay. So I've already partly answered the question of when or where MCDI has advantages, but let's look at some work we've done in the space to really refine that the answer to that question. I'll just say that CDI technology is not a new technology. It's been around for some years. In fact, the basic idea was developed in the early 1960s, and some very early work in the 60s really showed the technology worked at small scale. But in the ensuing 20 years or 30 years, there were major advances in materials, the electrode materials, in control technology that really raised the profile of this technology to be at a point where it could potentially be developed at larger scale and used for industrial use. And so in the last 10 years, there have been major advances, and advances also, for example, in using membranes to cover the electrodes, which aid salt removal and improve performance. As I mentioned, control technology, better electrode materials have all contributed to a point where the technology looks very promising. Well, so if it's so promising, why isn't it or hasn't it been commercialized? Well, there are a couple of companies internationally that are doing well out of CDI. One of those companies is Waite, a Netherlands-based company that also have production and sales in the United States. And Waite are doing quite well in this area, especially in applying MCDI to particular applications, small-scale use in coffee machines and household use, but also in areas of water cooling, evaporation towers, and so on. They produced electrode modules like this. This unit has about 400 electrode pairs. It's about 1 meter long, about that sort of size in diameter, and is pretty effective. And we've been using their electrodes in our prototypes for the last 3 or 4 years. But we've also found ways to improve the technology in terms of the modules. So we are actually also developing our own modules at our centre in Yijing, and I show a schematic of one here. And we've now developed a pilot line to, in fact, make our own modules. That pilot line was opened in May this year. I show some of my Chinese colleagues, Wang Jia and others from Tsinghua and Harbin, HIT, when we visited the plant in May this year. And we're actually involving our students here from UNSW in helping design and optimize this plant through use of digital twins and so on to make our own electrode modules. So there's innovation in that area of electrode modules that we think will be important in our own products. The other area I mentioned is to actually couple use of solar power with this technology. And we are now making units that are powered by either solar or mains. We can switch between the two or use both because our units actually are run off batteries, and those batteries can be charged either by solar energy, as shown here in this unit that was trialled in Xinjiang province in northwest China, or charged by solar energy. And so this work, I think we were one of the first to actually power our units by this technology. It does require some pretty clever control technology, and again, as I said, battery storage to manage this, and that's described in this paper in Water Research by my colleagues. A third innovation that I think is going to be important in terms of energy efficiency is to recover energy. Now, when you charge the system, you consume energy to pull the ions onto the electrodes, but you create a capacitor. And a capacitor, as we know, is essentially stored energy. Those ions represent charge, it's stored. And if you're clever, as my colleague, Professor John Fletcher is, we can recover that energy when we discharge. Now, if you don't recover the energy, it's dissipated as heat pretty quickly. So when you reverse the polarity and the voltage ramps down to, in this case, 0 volts, that energy can be recovered. And we've developed a technology using these DC-DC buck boost converters to recover that energy. And again, you can read about that work in this paper in Water Research. So that third innovation, we believe, in terms of lower energy by this technology, is a step up. The fourth innovation we think is important and will be important particularly in future is use of artificial intelligence, digital twins to actually both control the technology, but also to optimize its performance. And so we've developed digital twins of our units with support from our colleagues here at UNSW. And I'll show you in a minute a video of one of our digital twins. And also, we can use these digital twins to obtain real-time data, and then with machine learning algorithms, use that data to then optimize control of the technology such that we improve performance in terms of energy use and treated water quality. Again, you can read about that work in these couple of papers that I show on the screen. But in terms of digital twin, let me just show you a small video.
首先，穿戴好我们的增强现实 AR 设备，启动我们的 AR 设备，调用我们的设备模型。该模型是基于远在澳洲运营的 MCDI 水处理设备开发的数字孪生体。这就是 MCDI 水处理设备的数字孪生体，我们可以通过操作对其进行移动、放大或者缩小。通过操作，我们可以对设备不同组件进行高亮显示，从而方便使用者直观地了解设备，并辅助后期设备的运维管理。同时，通过数字孪生体，可以采集 MCDI 设备的历史数据，并实时监测设备的运维情况。此时，我们观测到的是电极出水的电导率数据。最后，通过数字孪生体，可以远程操控我们远在澳洲的 MCDI 设备，此时该界面显示的是不同组件的实时运行状态及数据。我们可以通过下方的界面对澳洲的设备进行远程开闭及调整运行工况的操作。是我们基于 MCDI 设备开发的虚拟现实 VR 系统。通过该套系统，可以身临其境地体验 MCDI 设备，同时也可以实现对设备的实时监测及远程控制。 最后，通过心仪中心的3D 投影技术，可以给观众带来 MCDI 设备的沉浸式体验。
Okay, so I hope you can see that video clearly, but that gives you some insight into our digital twin using both AR and VR technologies. And we found it pretty exciting to develop those digital twins. And as I'll explain in a minute, a lot of our trials have been in remote locations, so having access to our virtual units has been very useful. Just a brief comment on machine learning. I won't say much other than that we can obtain the data from the pilot scale studies or real-time studies, and then use that data to train our algorithms or develop our algorithms to then optimize performance in future. But again, please read that paper if you'd like more information on the machine learning aspects to essentially convert our digital twins into smart twins for process optimization. Okay, so we've done a lot of work at lab scale, as most university researchers do, but we also recognize the need to test our units at scale under real-world conditions. And so issues like, can we design and build robust units? How much does it cost to make a unit? Can we operate these units remotely and in a reliable way? What are the O&M costs? And how reliable are these units in operation in remote locations? And how does performance of these real units compare with our design brief? And lastly, how does the performance and O&M cost compare with that of other technologies? So with the recognition of need to do this pilot testing, we've undertaken now 3 or 4 pilot trials. I mentioned one trial. The first one was in far northwest China, but we've since now undertaken 3 trials here in Australia. And I'm going to spend the next 5 minutes talking about a trial in central Australia. I show on the map there, the location is pretty much in the middle of Australia, in a place called Ali Kurrang. It's a remote Indigenous community about 400 kilometres north of Alice Springs in central Australia. So very remote. So here are some shots of getting to Ali Kurrang in the outback of Australia. The source waters are groundwater. The only source of water there is groundwater. And as is typical of many groundwaters, it's fairly brackish. This site is not so bad. The TDS is just under 1,000, typically 1,000 milligrams per litre. But the Australian Drinking Water Guideline for salinity is less than 600 milligrams per litre. Now, I can't drink this water. It's too salty for me. The water in Sydney is about 200 milligrams per litre. And so there's a need to remove salt from this brackish water. The water contains also, it's quite high hardness, so quite high calcium magnesium, which cause scale problems in hot water units, car radiators, and so on. It has high fluoride, shown here. And it also contains some uranium. Now, it is less than the AWDG value, but some communities around this area substantially exceed this drinking water guideline value of 17 micrograms per litre. So removal of these trace contaminants is also important in these central Australian regions. Now, we chose this site in part because there is another technology, and that is electrodialysis on site. So this site does have a General Electric's electrodialysis reversal plant, and we decided to place our unit there so we can do a direct comparison. And I show here the EDR units, and here's the EDR stack shown at Ali Kurrang. One of the big downsides of EDR is that scaling is quite a problem. In these hard waters, there's a need for acid washing of the electrodes and membranes, and I show here the acid washing facilities at that site. And getting acid to these sites is a major problem. It's expensive to truck acid to these sites. So we built the unit. It was built through COVID in Langfang, just outside Beijing. It wasn't trouble free because of COVID. Our team at CTET, especially Xunzhe Lev, managed the construction by the company in Langfang. We control technology is critical, and we had great support from a company Goldwind in Beijing to develop the PLC. We then shipped the unit out of Shanghai in January 2021. We took it to Alice Springs. We set it up at a wastewater plant there and undertook testing for around 3 months. And then we trucked it to this remote site in Alicante in September 2021. And I showed the team and trucking to that site. In phase one, we ran the unit pretty much as we'd expected to run it. That is, we charged to about 1.4 volts. We discharged to nearly 0 volts, as I showed earlier. Our goal being to decrease the TDS from about 1,000 ppm to 500, and to investigate performance of that unit, and to see how often we needed to use clean in place to clean the electrodes, how much acid we needed, and so on. And so in terms of results, it worked pretty well, but we found that the cycle, that is a charging, that the cycle time is the sum of the charging, discharging cycles, didn't last that long. So the cycle time in terms of seconds decreased over some hours. And that reduction in cycle time resulted in a decreased output. It didn't really influence the quality of the treated water, but it did decrease the water recovery. We found we could actually fix this by letting the unit sit for some time, a couple of hours, or in this case 17 hours, to recover. But we still found this decrease in cycle time. So real world, we hadn't expected this, but we found that this was happening. And realized it was because we weren't discharging completely. Now, the problem was that the divalent ions, which are quite high, as I said, in this water, didn't move out of those electrodes very quickly. And we had to actually discharge under negative current, a reverse current, to a negative potential. So rather than 0, we actually had to drop the potential to -1 volts in order to pull those divalent ions out of the electrodes. And when we did that, at least in the laboratory, we found we could actually maintain operations with no decrease in cycle time, as shown in the plot in the bottom, both for single electrode pair, but also for a module of around 400 pairs. So as I show here, we had to actually move from this original operation, shown on the left, to discharging to -1 volts, as shown here. When we did that, we were able to go from this sort of decrease in cycle time through to this much more robust, pretty much uniform cycle time. And I show here the operational procedure. So here's our discharge to positive voltage or near 0. We stop flow during discharge, so there's a large spike when we turn the flow back on to remove the brine. Here's the applied current, so 100 amps, drop to -100 and so on. But when we changed the operation to negative voltage discharge, we dropped it to 0 and then further to -1 volts. Again, stop flow here and that big spike in brine once we began flowing again. So effectively, we realized through this trial that we had to actually move into this negative voltage discharge in what we call phase 2 operation. And in terms of performance, the unit worked pretty well right through both phase 1 and phase 2. Though, as I said, the water recovery wasn't great during phase 1. So in terms of water quality, I show the results here. Here's our feed water shown in the upper portion of the diagram, these open squares, TDS around 1,000. We dropped it to below the drinking water guideline. The red triangles are the MCDI results. The blue dots are for the EDR plant, which gave better removal, but in fact almost too much. We didn't need to remove this much salt. We were satisfactory in pulling it out to below the drinking water guideline with the MCDI unit. Nitrate, again, meeting our guidelines. Fluoride, the same. Uranium, interestingly, we were able to remove a lot in the unit, though we realised actually that uranium was intriguing. Most of the uranium was removed, and I won't spend long on this, but in fact stayed on the electrodes. It actually became attached quite strongly to the anode because the major uranium form is actually an anionic form. This uranyl carbonate species that I show on the left-hand side. So there wasn't much removal of a discharge of uranium in the brine. So it meant that the electrodes were accumulating uranium over time. So there'd be need to actually manage those electrodes as hazardous waste entities because of the accumulation of uranium. In terms of water recovery, I show here that we did okay, but we were down around more like 60 to 65% during the phase 1 trial where we discharged to 0 volts. We could increase that to almost 80% by going to negative voltage discharge. There were some spots here where we were playing with the unit, but on balance, we found we could increase water recovery by that negative potential discharge. I will wrap this up now by going to my conclusions. Just this plot here, where we compare the cost. And here we take into account the energy usage, the acid usage, and the total cost of both EDR and CDI. We've had to scale up the analysis to 250 kilolitres per day to get a reliable comparison. But in terms of O&M costs, energy and acid, EDR is about 37 cents per kilolitre, compared to about 29 or 30 by negative discharge. Going to negative discharge adds slight energy increase, as you can see here, but we are still below slightly the energy and acid costs of EDR. In terms of water recovery, we are similar to EDR, and availability also quite similar. So in summary, I'll just say, is MCDI other energy desalination technology? Well, yes and no. It depends on many factors. It depends on the site and the nature of the source water at that site. It depends on the power supply. If you can use solar panels, you can certainly reduce your energy usage. It also depends on the development stage of the technology. MCDI still is at an early stage, and the cost will certainly decrease in the next 10 years. We've seen it with RO, dramatic reduction in costs. It'll be the same with MCDI. But I will say that for reliable assessment, it's critical to undertake testing at scale, and if possible at a site similar to where the technology should be deployed. So I'd encourage academics to get out of the laboratory and into the real world and undertake studies at this sort of scale to really validate the technology. And I'll also say that these new digital tools of digital twins and machine learning, in my view, have a great future for these sorts of electrochemical technologies. And with that, Bruce, I will finish up the presentation and hand back to you for any brief questions.